Hello, everyone, and welcome to today's webinar, Elucidating the Composition of CRISPR-Cas12f1 Complexes Using Mass Photometry. I am Julie Abbing of LabRoots, and I will be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Refine. To learn more, visit refine.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. I'd like to now welcome our speaker, Selgar Henkel-Heinecke, PhD student at the University of Leipzig. Selgar, you may now begin your presentation.
Thank you for joining this webinar today. I am Selgar Henkel-Heinecke. I'm at the Peter Debye Institute for Soft Metaphysics at the University of Leipzig in the group of Ralf Seidel. And I will talk today about elucidating the composition of CRISPR-Cas12f1 complexes with or by using mass photometry. So CRISPR-Cas effector complexes, so what are they? They are adaptive immune systems against invading plasmids or viruses. So protein, or more or less, they form a ribonucleoprotein complex with the RNA, which is here in light blue, and we have the protein here. So they form, first of all, a complex. This complex can bind via base pairing to DNA with the RNA, and then we have here the target sequence. And this spacer or target sequence can be programmed to target specific DNA sequences via this CRISPR or CRRNA or a gRNA-guided RNA. And therefore, it's a powerful tool for genome editing. So in nature, there are a lot of CRISPR systems, and they are very diverse. I just picked here three, more or less, the most famous ones. So first of all, we have the Cas9 here and the Cas12a, which are, as you see here, monomeric. So the protein complex itself is monomeric. And of course, they then form a bigger complex, but it's more or less monomeric. And we can have also, like for Cascade, which is a multimeric protein, or has a multimeric domain structure here. And also for nuclease activity, it has to recruit another protein, the Cas3. And as we see here, that the complex stoichiometry is diverging. And for further research, we picked then the Cas12 family itself to look at it, first of all, a bit more in detail. And so therefore we looked, or as you see here already, we have a very diverse family. I just picked here this 5 ones, so but you have also, you have from A to E and so on. There's also B, C, and so on and so on. So it's a big family. You see also they are very diverse in their size of the protein, of the RNA, what they are targeting. But what I all have in common is that they have a one-to-one stoichiometry if you look at the protein RNA ratio. And when you look a bit more into genome editing, you have a need for small proteins because they can easier or more easily transported into the nucleus. And so in that sense here, when you look at Cas12f, you have it's the smallest representative within this family. But the stoichiometry is still unknown, or was still unknown at that time. And we then used mass photometry in that sense as a fast method to obtain this composition. For those of you who just heard of mass photometry, I will quickly explain how it works. So we have incident light, which gets which is shined into the sample or onto the sample here, and then we have reflected light from the bare glass surface, and we have scattered light from the biomolecules, and this reflected and scattered light then interfere with each other, and this interference pattern is then proportional to the size of the biomolecule. And there's one more thing you have to to do before calibrating the system. No, you have to calibrate the system before you really get to measure the whole thing. So what you normally measure is, you cannot measure molecular masses, of course. You measure a ratiometric contrast. This ratiometric contrast decreases linearly with increasing mass. And in that sense, here we used a multimerizing protein as a calibration standard. And then we can use a very simple linear fit to obtain the from the ratiometric contrast the molecular masses. What we should have, or what we should keep in mind for the rest of the talk already, is that nucleic acids have a slightly lower molecular mass. The calibration is done with the protein standard. So this means, for example, for DNA, it appears only in such a spectrum with only about 80% of the expected or calculated mass. You calculate it. So what have we done before we actually get to the Cas12f systems? We used a known complex or system here from Cas12a from Acetylbacillus sulfooxidans, and so we have here a big size protein, over 1,000 amino acids. It has a calculated or expected mass of 151 kilodalton, and when we measured the protein alone, we got a nice peak around 150 kilodalton. It has a very small CRISPR RNA in comparison to the protein size. And of course, the stoichiometry was known from cryo-EM data. So you see here that the RNA is buried inside this very large protein complex, or protein itself. And so when we then mixed the protein with the CRISPR RNA, we had an expected mass of 166 kilodalton. We measured 167 kilodalton, which gave us nicely this this 1-to-1 ratio, which we were expecting as well. And then we thought, okay, we go further with this, and we look at the mass binary of the binary complex of Cas12f1 from Synthroformonas palmitatica. And there we measured also the protein itself with an expected mass of 57 kilodalton, and we got a measured mass of 59 kilodalton, which was in the expected, or in the in the range of the whole system. And so everything was fine. But when we measured then the binary complex, we expected, as before, a 1-to-1 ratio. So we were expecting something around 125 kilodalton as a main peak. But we got always a main peak around 180 kilodalton. So what we could see is that since we cannot explain the stoichiometry via a very simple 1-to-1 ratio, and so we then went one step further. We thought, okay, we have to measure the RNA mass directly. In that sense, there was the next big, big step in that sense. So we measured the RNA alone, and we got this. So why do we get such a not nicely shaped spectrum? So as you know, the glass surface is negatively charged, and therefore the protein adsorption is preferred. And if we use then nucleic acids, we get only a low number of events. So we therefore have to positively charge the surface. Then nucleic acid adsorption becomes is then preferred, and we get a high number of events. And as you see here, it's this and this are two spectrums of the same RNA, but here we barely got any counts, and here we have a lot of counts just from the y-axis already. And we see here that we have a mass of 62 kilodalton and an expected mass of 68 kilodalton. So here again, we see that nucleic acids have a slightly lower or show a lower or appear with a lower mass than expected. But also RNA and DNA differ a bit from each other. With this knowledge, we then went again to assemble the puzzle in that sense. So we had the measurement of the protein itself, we then had the measurement of the RNA, and we could dive into the effector complex again with all our informations. And that time we assumed a 2-to-1 ratio for the from protein to RNA, and we got this a few 1 or 2 months before we could, or when we were still in this process. There was a publication also on this stoichiometries or on the structure of these complexes, and they could show as well that we have 2 proteins here and 1 RNA in that sense. So we could nicely get the same information with mass photometry. And we went then one step further. We took our binary complex and mixed it with DNA to look if this binary complex, this 2-to-1 ratio in that sense, is also the active form of which is then targeting DNA. So we took a big piece of DNA with 250 kilodalton. This is calculated. We measured it on a positively charged surface, and we got 205 kilodalton measured. And when we mixed this all together, we expected a peak around 390 kilodalton, and what we see here is a peak at 390 kilodalton for a 2-to-1 ratio for the ternary complex consisting of protein, RNA, and DNA, which was also shown or just recently published in that sense in the same publication, where they also showed the complex, the ternary structure of the ternary complex. And this was all done for Monas palmitatica in that sense. We had more, and so we played the same game for the Cas12f1 complex of Acetylbacillus sulfooxidans. And I will not go too much into detail with the numbers this time, but we again measured the protein itself, the RNA itself, and we nicely got again for the binary complex the 2-to-1 ratio in that sense. And we went further on, again looking if the binary complex is also targeting DNA in that sense. And for one note again, we have from the calculated mass and the appeared mass, so again about 20% less. And when we look at the ternary complex, we again expected a 2-to-1 ratio in that sense, and here we got again a peak around this position, and again so we could resolve this 2-to-1 ratio with mass photometry. We had one last binary complex investigated from this time from an uncultured archaeon, and there again we measured the protein itself with the RNA, and we could resolve again this binary complex with a 2-to-1 ratio. And in that sense, it was very nice. And then in the end, if you have all the information how you can measure this, it was very easy and quickly done. A last example of how to get into the composition of such complexes, but this time with a different, with a slightly different situation. We got from our collaborators from Vilnius this transposase B, which has a mass of 46 kilodalton, and the problem was that it assembles with the RNA during gene expression. So there was no information about how big the complex itself was. We had an expected or calculated mass of the protein itself, but our collaborators wanted also to know what is the complex composition. And so a RNA measurement was not possible, and also, of course, there was no possibility to measure the protein itself. And all our collaborators, in that sense, later you can read this also in their publication in Nature. So what I did then to really get into the to reveal this composition, I looked at the desorption events. So what I focused so far in this whole talk was about the adsorption events, which appear with a positive or with a normal mass as you know it. The desorption events, due to mathematical correctness, or however you want to call this, it's just something mathematical that there is their negative sign. So we see what is going away from the surface, and in that sense, since we use a normal glass surface and not a coated surface, we can look what is going away from the surface as well as what is landing on the surface. And normally what is going away from the surface, if you have such a mixture, are the nucleic acids, not the protein stays there. So we can obtain even more, or in one measurement, you can obtain the information of the nucleic acid, more or less, without without having to measure the nucleic acid itself. And in that sense, I looked at this negative or at this desorption events, and we could then resolve this, because we see here, okay, they appear with 42 kilodalton. And when we then take into account that they normally have a slightly lower mass than calculated, we go into something perhaps 50 or 49 kilodalton. And then this whole thing here revealed a 1-to-1 ratio. So to summarize my talk, you have to keep some things in mind if you want to resolve such complexes with DNA, RNA, and protein, of course. So such ternary or binary complexes whatsoever. When you calibrate and use protein, think or at any time, or however you want to, however you calibrate the whole system, that they appear with slightly different masses. So in my case here, DNA appears with about 80% of the calculated mass, and RNA with about 95% of the expected or calculated mass. To really measure nucleic acids and to increase the event number and the resolution, you should coat your surface with polylysine before a measurement. And then you can, such stoichiometries can be resolved of binary and ternary complexes. And you can also, you do it like this, or as I showed you one slide before with the desorption events as well. But this you can ask me again later on. And I have to say, or more or less, that mass photometry in that sense is a very fast method to unravel such protein, DNA, RNA interactions. And with that, I'd like to thank you for your attention. And I would like to thank Refine for the opportunity to speak to you and to give this webinar in that sense. And furthermore, I would like to thank our collaborators from Vilnius and of course my group, the molecular biophysics group in Leipzig of Ralf Seidel, for the opportunity and the discussions about this whole topic here. And yeah, I'm done, and please don't hesitate to ask any questions. Thank you.
Thank you for that informative presentation. We will now start the live Q&A portion of the webinar. And if you have a question that you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen, and we'll answer as many questions as we have time for. Let's get started. Our first question is, how did you ensure that the binary complex composition is not the opposite, such as 2 RNA molecules and 1 protein?
Yeah. How do we do that? So to do this, we employed measurements using so titrations in that sense. So we I titrated then RNA, more RNA instead of more protein, and in that sense I saw the same composition, or the complexes itself looked the same, and the spectra looked the same as if I titrated more and more protein. So in that sense we saw that that the complex was the same. And on the other side, when looking at the desorption events we saw with more RNA, we saw that we got a lot more desorbing molecules than using with the protein. We didn't see any desorbing events. So in that sense, we solved this by titrating the protein with more RNA. More questions?
Awesome. And then, yes, our second question is, how can unbinding events be used to obtain masses of DNA or RNA?
Be used. Yeah, so I think in that sense it's yeah, so I will go to this slide one more time. Sorry, yeah. Okay. So in that sense, to obtain the I have to look at the question one more time. How can unbinding events? I am so I mean it's very simple in that sense. This what you see here, which is encircled in red. So these unbinding events, if you have a non-coded surface and use then a mixture with protein and nucleic acids, you will always get these high counts of desorbing events. And here you can use this. I mean, it's negative, but this is just something mathematical. It's nothing real, this negative thing. So in that sense, yeah, this can be used to obtain these negative, or the masses, not negative masses, but the masses of nucleic acid in the sense of, and then to obtain the composition as well.
Alrighty, we have another question that asks, the negative values in this case of the TNPB complex would imply that the RNA is falling out of the complex?
I think yes. This we didn't, also we went not too far into this detail. In that sense, I just got the samples from our collaborators from Vilnius, and yeah, I think, I mean, normally there will always be some equilibrium, having, of course, protein and RNA or nucleic acid just by themselves and as a complex. And I think in that sense, you really just see the desorbing of in that sense, since I mean the protein complex with the RNA then can be seen as some kind of coating, and then we see that in that sense some of the RNA can bind to this site and then desorbs again. And I think so in that sense we see just free nucleic acids, and I don't think that there is some kind of decomposition of the TNBP complex in that sense. So it's more like, it's like you see the free RNA which is not in a complex, just binding and desorbing again. And in that sense, it's also very small, so you would not see it. Or I mean, it's just like I told you before in the talk that they are not binding very well to the surface, and so this desorbing is more seen than the real binding. So I think I talked a bit too much about this, but I hope that I could give you an answer for this.
Wonderful. And then we have another question that asks, from my understanding, mass photometry is measuring the size of the particle and then using the density of the particle to calculate the mass. Can this method use to measure the size only? Can we use it to measure other nanoparticles like lipid or polyplex?
Ooh, good. I have to read the question one more time. What I can say is that we tried also in our group to measure DNA origami molecules to measure it. This didn't work so well, but I'm not 100% sure if they got it to work. But because I'm in my group, I'm on the protein DNA or in the CRISPR field, so this I cannot tell you. But to measure the size, yeah, you can measure the sizes only, of course. I mean, in that sense, but for other nanoparticles, I think this you should ask the team of Refine. They are more into this. Yeah.
Alrighty,
But,
wonderful. We
yeah.
have another question. Could you explain again how you reached the conclusion that the ratio is 1:1?
Yeah, of course. I think this is again regarding this TNPB. So the conclusion was, or how did I get to this conclusion? So I measured first, I measured the complex, which was assembled already, and I had this was the only information I got, and then I measured the 96 kilodalton, and the next step then was to look at the desorption events, which are here encircled in red, and from that, and then this is then the clear size of the RNA in this solution or in this complex, because this is protein doesn't there would be only, I don't know, a few up to, I don't know, 5 to 10 events, but not, I think this was like a few hundred, like 700, 800 events or something. So you would clearly see a difference if this was only protein or something which is, only protein. And in that sense, so this is clearly the nucleic acid in this case here, RNA. And if you then compare the size of the RNA to the size of the complex, and we knew that the mass of the TNPB was 46 kilodalton, we assumed from that that the whole or that the ratio of this complex is 1:1. I hope this is now answered.
Yes, and then we have another question that says, why can you not see desorbing of the whole complex at once?
I mean, you see, sorry, you see some. I will just go previous. Yeah, yeah. So now it's not in circle. I mean, you see here at the 100 also, and a bit lower, so at the negative side. You see also some events. What I told you so far. So there are some minor desorbing events, of course, of the whole complex itself. I think, but I'm not 100% sure. A colleague of mine, she also did measurements with a coated surface, measuring protein DNA complexes, and I think there she could see some or more desorbing events of such a protein DNA complex, but for me this was not the question in this experiment. But you will, or you would see the complex itself if you would use a coated slide with polylysine in that sense.
Alrighty, and then for gRNA, can we use nucleic acid calibrants instead of protein calibrants? Will this yield more accurate mass values?
Yes, yes. This, if you're just interested in measuring gRNA and not in measuring complex or complexes with different composition, then you can always use a calibrant. So just like a nucleic acid, or if you even have it, you could use a RNA as for your calibration. This would be even more accurate. So it was, for me, it was I had to decide, or to say like I have to calibrate with one of those three in that sense. And I was then saying, okay, I use protein and measure everything then one time as a only measurement to obtain these masses, and to know, okay, what is the difference between the real value and the measured value. And so I got this inaccuracies in that sense. But yeah, it's up to you what you use for protein or for calibration.
Alrighty, and it looks like we have time for one more question, and it is the surface modification with polylysine easy to carry out?
Yes, the surface modification, I think it takes like roughly 1 minute or something. It's done very easily. So you have your prepared, I think it was 1 or 10% polylysine solution. But this is always according up to a protocol from Refined. So it's just you add a drop of on one of your slides, and then you just put two slides together like a cross, and then you have in the middle your polylysine, and then you just dry it, and then just dip it into water one time to wash out excess polylysine, and then that's it. So it's very easy, very convenient, and yeah. So in that sense, it's good, good and easy.
Thank you, Selgar. Do you have any final comments for our audience?
Yeah, use mass photometry in that sense. I'm in the beginning, I was also a bit yeah, okay, how this is all working, but it's easy. It's and what I really like is that you don't need any labels like fluorescent labels or spin labels or whatsoever, and you can easily get the purity of your solutions, and equilibria, and how does it really look in your solution. Sometimes you don't know it, and this was also for me, the information were very, very important for my single molecule experiments, which I employed up on the information I obtained via mass photometry.
Wonderful. Thank you again, Selgar, for your time today and your important research. We would also like to thank LabRoots and our sponsor, Refine, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it is available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.